Hello, good afternoon. Today I originally planned to go over hypothesis testing, the starting hypothesis testing for today. But I realized two things, that the material that I will go over today already well presented in lesson 18 and 19. So instead of spending the time going over things that you can just watch during the weekend, what I will do today instead is to go over one more previous test from the past. Okay, now don't forget that your test 3 is this Wednesday. The procedure is the same with the previous two tests, test 1 and test 2. We will start our test at 4:30. So from 3 to 4 o'clock, I have my office hour as usual. And from 4 o'clock to 4:15, I basically continue my office hour. Maybe I write it down, give me a second. So this Wednesday, May the 5th, is your test 3. Okay, from 3 to 4 p.m. is my office hour. If you have any question, feel free to ask me during that time. From 4 to 4:15, basically continuation of my office hour. And then after 4:15, we will start the sign-in process. And basically up to 6:30 p.m. That's sign in and test. Now, just like before, 6:45, your test should be submitted. Test should be fully uploaded. By this time. Okay, let's have that the timeline clear on Wednesday. Now on Monday next week, we will start hypothesis testing. Now, but the framework for that hypothesis testing already very well, I believe is already very well described in my lecture video. So please, please, please do me and you a big favor by watching these two videos here, at least by Monday. At least these two by Monday. If you want to watch more, go ahead. Okay, which more, Thomas? I will show you the list later on, but at least from this one and this one. Now, I said here the second half of lesson 18. If you click that, you start from after 1 hour. So you see the minute here, right? Start from the beginning of the, so from here. So 1 something. Okay, so basically from the first hour, first minute, I want you to watch that, okay? Now then, after you've watched that one, then watch this lesson 19 also. Now, it will be also nice while you watch those lecture videos, okay? So you don't need to watch from the very beginning of lesson 18. No, start from the end of the first hour. It's good enough. Okay, now in between, this is the accompanying handout to help you. Okay, now then, if you wonder, Thomas, you say if we can watch more, where should we watch it? Then you go to announcement 5. So today we're supposed to do that lesson 18, right? But I postpone it until next week. Okay, now next week, Monday, we will go over lesson 18 and 19. 18 and 19. Okay, but I will do problems instead of going over the technicality again. Now, the framework is very, very important, and that's what we will use for pretty much the rest of this semester. In other words, for the next 3 weeks, we'll always use that framework, okay, of doing hypothesis testing. Chapter 10, chapter 11, all need that framework, okay? Yeah. And then we will have linear regression. We will do that maybe like the last week of our class. But we are now on hypothesis testing, and it requires a very, very strong knowledge in using the framework. Okay, now what I will do instead today, let me go back. Sorry, let me go back to my discussion board. Yeah, what I will do instead today is to go over one test. Oh, by the way, this Wednesday you have a test, and I hope I can finish grading your test very, very soon. Hopefully by Friday. Okay, but this Saturday is the last day to drop the class. So I purposely make it in a way that your test 3 is done before the drop deadline, in case you want to use your test 3 to decide whether or not you should drop the class. Now, it is not my intention or my interest at all for you dropping the class, okay? But I need to mention this because after this weekend, after this Saturday, then you cannot drop the class anymore. Not even me dropping you. That's what I'm saying. Okay. After the technical wording the administration use is no more transaction should be done. They use the word transaction. No more transaction should be done after the drop deadline. In other words, after this drop deadline, you will get either A or B or C or D or F, not a W. Okay, you cannot get a W. Even I cannot do that. Okay, under very, very special circumstance, you may be able to get a W, but for that one, I think you need to make an appeal all the way to maybe even the dean of academic affair or vice president. Okay, basically it's out of my hand after this weekend. Okay, this is true not only for my class, this is true for all classes for every semester. The last day to drop the class is the Saturday of the 12th week. This is week number 12, right? Now the end of this week is the last day to drop the class. Okay, the thing is like some students after the test, they don't really check my feedback on their test. They don't even think about the drop deadline. Then the next week, week 13, they look at their score. Oh, I'm not doing well. Can I still drop the class? And at that time, whatever you think, nobody can do anything. Okay, not either. In the past, I have students kind of like blaming me. It's like, you're the teacher. Why can't you do anything? No, there are some rules I myself have to follow. Okay, and that's one of the administration rules that I have to follow, that after week 12, I cannot drop anybody. Okay, and this semester, just like last semester, I have not dropped students for not attending the class. Of course, if you don't take the test twice, and I drop that student, right? Okay, but if a student not attending the class, as long as that student actually take the test, whatever the grade, even if that person get a 0, I will not drop that student, because what? I know some students actually in need of financial aid. Okay, and that's maybe the reason they keep the class, right? That's why I don't drop students. But at the same time, I don't want you to get an F and required by the Department of Education or whoever lend you the money that you need to return the money later on. Okay, that's not what we want. That's not our interest, not my interest, not your interest, right? Okay, that's why I warn you about this. Okay, as far as I know, if you have financial aid, if you get financial aid, you can drop the class in week 12 without any need of returning any part of the money. That's what I know. But of course, you should confirm that with financial aid office. Okay. Now that's about our discussion. So please let me remind you again. This weekend is the last day to drop the class. This Saturday, maybe Sunday, but don't wait until Sunday to do that, because usually the system is being updated during week 12 also. So this our system may say the last day to drop the class is Sunday, maybe. Okay, but on the same Sunday they usually do some kind of upgrade on at the end of week 12. Okay, so suddenly on Sunday, students who want to drop the class, they cannot drop the class because the system is being updated and the system is down. Okay. Also, this after this weekend, Monday, this weekend, after this weekend on Monday, we will go over hypothesis testing. On Monday, I will assume you have watched these 2 lecture videos. Okay, that's my assumption. That's what I do in return of going over another one test today. Another reason why I want to go over one more previous test today is because of the following. When I went over spring 20 test 3, so let's go back to what I wanted to do. See on our last discussion, right? I gave you, we went over 420, right? We went over 420 and I gave you the solution there together with the video, okay, in the recording. And I gave you spring 19. Is it spring 19? No, I think spring 20. Hold on. Spring 20 test 3 is very similar to very similar to fall 21. I don't know about this spring 19 though. Let me take a look. Is it very similar also or different? Oh, it's very different. Okay, good. Okay, good. So I thought it's the same. I'm sorry, because at East LA College I went over with them spring 20. And then when I went over with them, I realized, hey, you know what? Why the test is very similar to what I went over with West LA College students. So fall 20 test is very similar to spring 20 test 3. Okay. Good that I gave you spring 19 instead. Okay, you definitely have something to study from there. But the problem with spring 19 is it does not have confidence interval question. Okay, while your test 3 will include confidence interval. Okay, 9.1, 9.2, 9.3, and confidence interval. Basically, confidence interval for mu with sigma known or unknown. Confidence interval for population proportion and confidence interval for population variance or population standard deviation. Okay, so that's why today I want to go over winter 21, what I went over, what I gave to my students during this winter at the beginning of this year. Okay, I hope then you have 2 different sets of tests that includes confidence interval. Okay, and spring 19 basically as a supplement for other topics that not including confidence interval yet. Okay, now let's start with this winter 21 solution. US female lifespan is normally distributed with a mean of 81 years, 81.0 years, and standard deviation 15.9 years. Okay, so it's normally distributed. Let X be a US female lifespan. Now this X is normally distributed with mean 81.0 and standard deviation 15.9. So the variance is 15.9 squared. Now part A, find the probability that a randomly selected female will live longer than 85 years. Probability that X is more than 85. That's normal CDF. It's more than 85. So if you have a normal distribution, the mean is 81. Okay, more than 85 means start from 85, go very far to the right. Okay, so normal CDF 85, E99, 81.0, 15.9 for the standard deviation. Okay, probability notation first, and then calculator notation, and then the calculator result. Now use your calculator, normal CDF 85, lower bound, upper bound E99, the mean is 81.0, standard deviation 15.9. I get 0.40068, so 69. Okay, now you notice that I give 3 points here. Now those 3 points are for the probability notation, 1 point, calculator notation, another 1 point, and calculator result, another 1 point. Okay, now if you use 0.40068 here, that's half point off because of the rounding. Now, why, Thomas, you've worried so much about notation? Because correct notation enables us to formulate the situation in a more precise way. For example, part B, 90% of all females live longer than K years. Find that K. So let's say this is the normal distribution for the lifespan. 81 is the mean. Okay, now longer than K years, 90%. So probability that X is greater than K is 90%. However, we will use inverse norm here, but inverse norm can only take care the area to the left. So let's rewrite this probability such that we look at the area to the left instead. So probability that all female live not longer than K years is 10%, right? Which is 0.1. Now then K is equal to inverse norm 0.1, that's the area to the left, the mean 81.0, standard deviation 15.9. Now then use your calculator to find the number. Inverse norm 0.1, 81.0, 15.9. So that's 60.62333 years. Okay, so approximately 90% of all females live longer than 60.6 years.
Professor, sorry, did you post this test already? Because I didn't see it on the.
Oh, okay. You know what? Maybe not. Let me post it first. Give me a second.
Okay, thank you.
Okay, I already post. I forgot to do that earlier, but I post the blank test actually on our discussion board. Okay, it's here, so you can print it out and try to follow me during with the lecture. Okay, when I go over that, let me go back to the notes. Part C. A group of 6 females are selected at random. Find the probability that the mean lifespan of these 6 females exceed 85 years. So instead of only 1 female, we have the mean of 6 females. According to central limit theorem, because the underlying distribution already normal, then the sample mean distribution will also be normally distributed with the same mean, with the same average, yet the variance will be the same variance divided by the sample size. Okay, now find the probability that the average, the mean lifespan of these 6 females exceed 85 years. Now that will be, the mean is 81, right? You want the mean to be more than 85. So this will be normal CDF lower bound 85, upper bound E99. The mean is 81.0, standard error 15.9 over square root of 6. Okay, let me move that a little bit to the left so that I don't go into the other question. And then I use my calculator. Normal CDF, 85 is the lower bound, upper bound E99. The mean is 81. Standard error is the original standard deviation divided by square root of the sample size. That will be 0.26887. Okay. Then let's see part D. A group of 6 females is selected at random. Find the probability at least half. So this is the number of females the number of these 6 females have lifespan exceeding 85. It is not normally distributed for sure. Why? Because the distribution for the number of incidents, or in this case, the number of people, will not be normally distributed. It's not continuous to start with, right? Okay, the number of people has to be 0 or 1 or 2 or 3 or 4 or 5 or 6 in this case, right? So either one selected female has a lifespan exceeding 85 years or not, right? Okay, so let's define a new variable. Let y be number of female with lifespan exceeding 85 years. Okay, now this y will then be binomially distributed. The number of trial is 6. Okay, probability that one female has lifespan exceeding 85 years is 0.40069 as already computed in part A. Now what we want is probability that at least half, means at least 3 of these 6, right? At least half of these 6, that's 3 or more. But for binom CDF, we cannot count from 3 to infinity, or in this case 3 to 6. We need to compute the complement, which is 1 minus probability that y is at most 2. Okay. If what you want is 3 or greater, then the complement will be only up to 2, right? for discrete distribution, for discrete random variable. For continuous random variable, then the complement of greater equals to 3 is less than equals to 3. If it is continuous. For discrete, you need to consider if it is not at least 3, then it will be at most 2. Okay, this is 1 minus binom CDF. Number of trials is 6. Probability of each success, one success is this, up to 2. Then you use your calculator, binom CDF. I hope you know where to find it. Okay, 6. Number of trials. Probability of a success is 0.40069. And you need up to 2 successes. So I get 1 minus 0.54289. Subtract it from 1, that will be 0.45711. Okay. That's for part D. Let's see part E. If the average lifespan of 6 females is at the top 10%, so it is at the top 10% for X bar 6. X bar 6, it's on the top 10%. So what is the minimum average lifespan or do these 6 females have? Let's call this K. Okay, the probability that the average lifespan of these 6 randomly selected female to be greater than K is 10%. What is K? Again, we cannot compute that directly because when we use inverse norm to find that K, the area has to be the one to the left, not area to the right. So let's do adjustment first. This is probability that the average lifespan of this randomly selected 6 female to be less than K is 90%, right? So K will be inverse norm. The area to the left, 90%, 0.9. The mean is 81.0. Okay, and standard error will be 15.9 over square root of 6. Okay, we use this distribution here. Okay, we use that distribution. Now then, you use your calculator to compute that inverse norm. Area to the left, 0.9. The mean is 81. Standard error, 15.9 over square root of 6. So the average of this, the lifespan of these 6 female should be 89.31874 years. Okay. Now, of course, it feels strange to keep the number with 5 decimal places in that situation. Well, but this is a stats class, so I make it as accurate as possible, right? When you write it in newspaper or you talk casually to somebody, you may just say 83.3 years. You know, that should be good enough. But in my test, then round it to 5 decimal places. Okay. That's for part E, page 1. Let's go on to page 2. Two percent of our population contracted a disease called statistitis. Actually, to tell you the truth, the number I use here actually fits the situation for COVID-19. At least at the early stage last year, like around March or April. But I also understand if I use COVID-19, some students have some deep wound, some trauma with that. Okay, so I changed that to something else. Okay, in the past, I call that some other disease, statisticitis, or T vaccine, or something like that. Okay, now 2% of our population contracted this disease. So it's you have disease at 2%. Okay, now of course 98% doesn't have that issue. Okay, now a new test is developed to detect this disease. It results in 3% false negative. What is false negative? False negative means you are tested negative, but it is false. This is false negative. You actually have the disease, yet it shows negative at the rate of 3%. Now that implies that you are tested positive correctly, true positive, at 97%. Is it right? And 5% false positive means you don't get COVID-19. Oh, I'm sorry, you don't have statisticitis yet, you are tested positive. That's 5% rate. Okay, that's false positive. Now false negative, I'm sorry, true negative, therefore is 95%. In technical biomedical biomedical terminology, or some statistic terminology, we say that this is the specificity. I forgot what's the terminology for this. Start with S also. Specificity. Sensitivity. So this is the sensitivity. This is the specificity. So when they say, instead of saying 3% false negative and 5% false positive, they may say this is 97% sensitivity and 95% specificity. Okay, so those are just the different terminologies being used in different fields. Okay, now the thing is, once you understand what those terminology means, then you can actually build this tree diagram. Okay, so let me pinpoint again. This 3% false negative refers to this. Okay, 5% false positive refers to this. Okay, let me erase the blue, the yellow color. Oops. Now that's the tree diagram. Let's go on. Find the probability that a randomly selected person is tested positive. So what is the probability a randomly selected person is tested positive? When I went over this test with the students there in this winter, a student then later on say that, oh, Thomas, if this is what happened with COVID-19 tests, then there must be a lot of people tested positive while they actually don't have it. You see what I mean? Okay, and that's actually encouraging, such encouraging in a way that, to say encouraging in the sense that a lot of people are tested positive, but they actually don't have that COVID-19. Okay, we'll see the result later on. Okay, after we work this problem out. What I want to say is this, that the result from CDC, Center of Disease Control, also shows that while COVID-19 last year is very, very high, for some strange reason, the number of people getting flu during flu season is very, very low. The number of people getting flu suddenly drop very sharp. But those people that contracted COVID-19 increased very high, such that we suspect that there are some people tested positive for COVID-19 actually catching a flu. Okay, actually catching a flu. Now, I am not saying COVID-19 is just a flu. No, that's not what I'm saying. Okay, to say that COVID-19 is a certain flu may be correct, but I prefer to separate that as another new type of flu. Okay, but it's not just a flu that we have before. Now the thing is, even flu that we had in the past, some of them actually caused by coronavirus. Okay, but coronavirus, there are a lot of type of coronavirus. One of them is the one that caused COVID-19. Okay, but there are a lot of coronavirus. There are a lot of coronavirus. The SARS, if you know SARS that we had like around 14 years ago, that's also coronavirus. I mean, that's a virus with corona. Okay, but not the same type with the one that caused COVID-19. No, it's different type. That's why they call that SARS-CoV-2 for COVID-19. It's different type, but it's both of them corona. Okay, and coronavirus already around, different type of coronavirus already around, and there is a chance that the COVID tests that being administered to us also caught people who get who caught coronavirus, but not COVID-19 one, and they were categorized as COVID-19, misidentified. Okay, misidentified. That's the situation. Now, the reason this becomes my interest and ask this question in my tests in the winter is because that I personally want to see more. If somebody misidentified as having COVID-19, then their chance of survival supposed to be higher if we use the treatment for regular flu that we had in the past. Let me put it this way: if that person actually catching COVID-19 and was given treatment for COVID-19, then it's supposed to be okay, right? I mean, that's the right thing. If you get COVID-19 and you get treated with COVID-19 treatment. But what happens if you actually get flu, which is misidentified as COVID-19? If you are treated with COVID-19 treatment, that could be that. I don't know. I mean, that I don't know, but it could be really bad if you are misidentified as COVID-19, having COVID-19 instead of just a flu. Okay, don't get me wrong. Some flu are really bad. Okay, so I'm not supposed to say just flu, but some flu are so bad such that if you treat it incorrectly, then it could be deadly. Okay, that's why I brought this up. Okay, that's why I brought this up. Now let's go back to the numbers. Probability that is tested positive is either going through this branch or this branch. Okay, that's for tested positive. So this is probability of having that statisticitis and tested positive plus probability of not having that disease statisticitis and still tested positive. That will be 2% times 97% plus 98% times 5%. To the decimal, 0.02 times 0.97 plus 0.98 times 0.05. Using my calculator, 0.02 times 0.97 is 0.0194 plus 0.98 times 0.05, that's 0.049, which when I add, give me 0.0684. So you will see that approximately 6.8% of the population will be tested positive, regardless that person actually have statisticitis or not. Regardless that person have statisticitis or not. Now, part C. Given that the person is tested positive, what is the probability that person actually have that disease? So if you replay this, but you change the statisticitis to COVID-19, for example, what is the probability that you actually have that COVID-19 if you know you are tested positive under the following situation, under this, all these assumptions here? Then this will be probability that you have that disease and tested positive divided by probability that somebody is tested positive. That will be 0.0194. Notice that what we had on the top is actually this part here. Okay, we already computed earlier. Over the probability somebody tested positive is 0.0684. 0.0194 divided by 0.0684. That is 0.28363. So of those tested positive, only 28.4% of them actually have the statisticitis. Okay. Around 72% of them don't have that disease. But of course, we also still need to worry what happens if somebody's tested negative, yet they actually have that disease. Okay, but for now, the one that scare everybody, especially last year when we see the COVID-19 increases so fast, we were so worried. It's like, why so many people get it? You know, now we realize that it is possible that some of them tested positive with COVID-19 while actually they have another type of flu, which happens to be coronavirus also. Okay. Now, I don't know the inner work of the COVID-19 test that we are using right now, but the number I get here coming from UK. Okay, so not from America. What I know, the PCR test that we use here is the same to the PCR test we use there around 6 or 9 months ago. Okay, now the PCR test being used right now may already has more accuracy that target the DNA of COVID-19 specifically. Okay, in other words, the test we have right now may be more accurate. Okay, but that's what happened last time. Okay, now part D. Of 120 people tested positive, find the probability that more than half of them are not contracted. Okay, let Y be number of people not contracted. Now this Y will be binomially distributed. Number of trials is 120. The probability that that person, even though tested positive but not contracted, is 1 minus the probability that person actually contracted, which is something we get here, 28363. 1 minus 0.28363. Yeah, you can make it right. So this will be binomially distributed. Number of trials 120. The probability somebody tested positive, not contracted, given that person is tested positive, is 0.71637. Okay, now the probability, the number of people not contracted to be more than half, so more than 60, more than half means more than 60 out of 120, is 1 minus probability that Y is less than equals to 60. This is 1 minus binom CDF. Number of trials 120, probability somebody tested positive but not contracted is 0.71637. To be more precise, some probability somebody not contracted, given we know that person is tested positive. Okay, that is, and then up to 60. So this is, let me see, binom CDF, 120, number of trials, 0.71637. That's the probability somebody not contracted knowing that person tested positive, comma 60. That is 1 minus 0.12345667. Okay, this is, I get this, I get 4.649 something, let me call 5 times 10 to the negative 7, which means the 4 here is on the 7th decimal place. Okay, but when I subtract this, then you see it's basically rounded to 1.0000. If I round it to 5 decimal places, then the probability that more than half of them not contracted is actually 1. We are sure that of 120 people tested positive, more than half of them actually not contracted. We are sure. We are sure. Now, this test seems to be good, right? This test seems to be good, that if you actually have that issue, you have that disease, 95%, the 97% of the time, it will show positive. If you don't get that, then 95% of the time, it will show negative. Okay, but the accuracy of a test is not being seen that way, though. Okay, the accuracy of the test is actually being seen in the following way. Okay, you need to see what is the probability. This is another topic. What we are interested in is actually if you are tested, if we are tested positive, what is the probability we actually have that disease? And if we are tested negative, what is the probability we don't have that disease? In this situation, notice that if you are tested positive, the probability you actually have that disease is actually less than 30%, right? It's less than 30%. Okay, imagine if we suddenly come with a situation where you have a test right? A COVID test, for example, that you should get scared, even more scared, if you are tested negative because of this kind of statistic. If you are tested positive, the chance that you actually have that is only less than 30%. But if you are tested negative, the chance that you actually don't have it is also around 30%. Do you think that's scary? It's like the test shows the opposite instead. Okay. Now, of course, I'm not saying that we should question the PCR test. Like if you are tested positive, if I am tested positive for COVID-19, then I need to quarantine myself, okay, and seek help, okay. Yeah, but at the same time, don't be sad. A little fact about this COVID-19, I have to say, consider this a bit out of topic, and this is not the substitute for your doctor's advice, okay. But a lot of sun bath, not to the point that your skin get burned though, okay. When I say sunbath here, do not use sunscreen. No. Okay, you need the vitamin D, infrared, and a little dose or ultraviolet from the sun. A very little dose of ultraviolet from the sun to help you healing. Okay, sunscreen blocking those ultraviolet and reduce the vitamin D that comes into your body. Okay, now also drink and eat hot stuff only, nothing cold. Okay, and drink as much as possible. Just drink hot stuff, hot drink as much as possible. Some people say hot tea helps. Some other people say hot coffee helps. It's about being hot. Why? A lot of virus actually die, not only virus, bacteria also dies when it is exposed to heat, okay? Especially flu virus in general. Flu virus actually progress quite fast when the weather is cold, right? Okay, so when you change the environment becomes hot, it doesn't have enough time to adjust themselves. And another reason is when you drink hot stuff, okay, you basically try to flush the virus from your body. Okay, that's another one. And the last one that I really need to emphasize is be or stay happy. For some strange reason, this virus actually works very well. How to say that? If you are being happy, you know, if you are getting excited, you know, your body produces something called, I forgot what's the name, I forgot the chemical name. It's some kind of hormone or enzyme that makes the virus cannot grow fast. Okay, you need that. You need that. Okay, so on the top of vitamin D in infrared, vitamin D, vitamin C, vitamin E, whatever your doctor asks you to get, you know, get them. And it's a lot of sun bath. Okay, drink a lot of hot stuff and eat hot stuff also. And please stay happy. Okay, I have seen people who, I have known people who quarantine themselves, they isolate themselves, and during their isolation, they actually play games, watching Netflix, and they actually recover really fast. Okay, so I'm not saying this because of my hypothesis only. I have helped some people, sending them vitamins, medicine during their isolation, and I send it for free to them. Okay, some of them in America, some of them in Indonesia. In return, I expect them to give me their experience. Okay, what happened to them, what they did, what their doctor gave them, and how they recover. Okay, so far people that I come to my attention and I help, none of them actually pass away yet, which is a good thing. Okay, that's how I know that vitamin D, vitamin C, a lot of sun bath drink hot stuff and be happy is necessary. Okay, of course, this is not a substitute of whatever your doctor say. Consider that as a supplement. Okay, whatever advice I give you here, your doctor's advice supposed to supersede what I say here. Okay, now let me erase this. And we all want this pandemic to go away as soon as possible. You know, it takes a lot of toll in not only in our health, it's also in our mental health, if you think about it, right? We get locked down for too long, we stay home for too long, so less association to socialize with other people. Okay, and not to say that the economic financial havoc breakdown that a lot of students that I see experience. You know, like students depends on part-time work, and part-time workers are actually the first in line when they need to send home. You know, so I'm saying this out of concern of a lot of my students. I myself actually fine. If you think about it, I teach from home, right? But I worry a lot about my students though. Now let me go back. Okay, let me go back. Use the result we have from ABC especially to complete this contingency table. From the information we have above here, okay, we know that 2% actually have this disease. So of those with this disease, a total of 2% of them have this disease, which means 98% not having that disease. Now we know that from what they tell us, right? Now, how about tested positive? They are 6.64% tested positive. Where did you get that from? From here. Oops, I'm sorry. I'm sorry, I need to erase this. I get it from here. Tested positive, 6.8%. Okay, now it means the one tested negative is 93.16%. How do you get that, Thomas? This should add up to 100%, just like this is supposed to add up to 100%. Okay. Now, tested positive and with disease, according to our computation, this is the one tested positive with disease, 0.0194. Okay, so it is 1.94% of the population actually tested positive and actually with the disease. Now, what percent tested negative while that person have the disease? Whatever, add up to 2%, right? 0.06%. Oh, that's a very small result, huh? How about those tested positive but actually don't have it? And it will be this one here, the one that add up to 6.84. Okay, that will be 4.9%, I believe. Yeah, you can try doing this. 6.84 minus 1.94. You see what I mean? You will get 4.9%, right? And the one here, either you find out the difference here or you find out the difference here, it will give you the same number here. Okay, that will be 98% minus 4.9% will be 93.1%. So 93.1% of our population actually without the disease and tested negative. Okay, now that's for question number 2. I'm sorry I relate this a lot to COVID-19 because I want us to realize that even the PCR test that we took before has some error. Of course, I'm not saying that you should not believe it, okay? But I'm saying that later on they found out that the number of people exposed to say that tested positive and actually have it is actually much lower than what we thought. Okay, much lower than what we thought. Okay, but we were too panicked though. I don't blame the government or whoever for that. No, we were too panicked last year. Okay, we do everything we can to protect whoever we have. Now, number 3, I will do this one more problem and then we take a break. Okay, the number of people living in a 2-room apartment is a random variable x with the following distribution. Of course, the total has to be 1, right? So when I add these, I will get 0.85. Means 1 minus 0.85 is 0.15. Okay. Now then, find the average number of people living in a 2-room apartment. Extend the table above and provide your result below. Make sure you use correct notation. To find the average, I will extend with px, whatever the result I have here, that's the mean. Okay, so this is 0.10, 0.80, this is 1.05, this is 0.60. If I add all of these, what will that be? 9, that's 1.95, 2.55. I hope I don't make miscomputation there. Okay, so the expected number of people living in a 2-room apartment is 2.55. You can also use mu. Yeah, you can use expectation of x, you can use mu sub x, or you can also just use mu, that's fine. Not x bar, not x bar. Okay, don't use x bar. Part B, the standard deviation find the standard deviation of number of people living in a 2-room apartment. Extend the table above, then provide your result below. Make sure you use correct notation. I will do x squared and then px squared. 1, 4, 9, 16. This is 0.10. P times x squared is 1.60 here. 9 times 0.35, I don't know. 0.35 times 9 using my calculator is 3.15. And 16 times 15 is 2.4. So that's 0.1 plus 1.6 plus 3.15 plus 2.4. That is 7.25. So the variance will be 7.25 minus 2.55 squared. I get 0.7475. That's the variance. So the standard deviation is the square root of that number. That's 0.86458. As for notation, variance of x, you can use sigma squared of x. You can use sigma squared subscript x, or you can just use sigma squared. Okay, now standard deviation, however, you can use sigma parenthesis capital X or sigma subscript X or simply sigma. Okay, now standard deviation does not have this notation. You cannot use SD parenthesis X. Most probability and statistic instructors do not accept that notation, even though we know what you mean. But the purpose I say that make sure you use correct notation here is because I want to give you extra credit, right? It's supposed to be an easy one, just the notation, not too hard. Okay, but you need to know which one. The thing is, the sloppiness, some students are so sloppy that they don't even think about or know the notation for population standard deviation. Okay, the standard deviation of a distribution. Part C. An apartment complex consists of, it's supposed to be with an S here, consists of 250 apartments, all of them two-room apartments. Find the probability that there are more than 520 people living in that complex. So N equals to 250. What is the probability that the total number of people living there is more than 520? But if the total is more than 520, it means the average of those 250 apartments is 520 over 250. You see what I mean? The total number of people, more than 520 people, right? The total number of people. But there are 250 apartments there. So each apartment on average, the average for each apartment will be 520 over 250 or more than that. In this case, more than 520 over 250. Okay, now what is X bar 250? It is, the sample size is more than 30 already, right? So by central limit theorem, it becomes normally distributed with the mean, the same mean we had above, 2.55. Okay, and the variance will be 0.7475 over 250. Okay, the original variance divided by the sample size. Now then, this becomes normal CDF 520 over 250 is the lower bound, upper bound E99. The mean is 2.55. The standard error is the square root of 0.7475 over 250. By the way, this is also can be said 0.86458 over square root of 250 because the square root of the variance is this. Okay. Now then I will use my calculator. Normal CDF 520 over 250 as the lower bound, upper bound E99, the mean 2.55, and standard error is the square root of 0.7475 over 250, still under square root. This is equal to 1. What is the reason we want to talk about this, Thomas? How this question apply into my daily life? What I had in mind when I asked this question. So suppose we already have this result here. Do not underestimate these statistics. I should say this parameter. Don't underestimate this distribution. Why? Because in case of an earthquake, how many people should you account for if you have a complex consisting of 250 apartments, each of them two-room apartments. Okay, now I don't think we have such kind of complex in LA, but the apartment I live in before I get my house, the apartment I live in consists of 160 apartments. Okay, in that complex, there were 160 apartments, all of them two rooms. Okay, some of them studio, some of them only one room, but around 160 of them actually two rooms. So in case there's an earthquake and the buildings collapse, then how many people should we account for? Suppose we found 520 people still alive, right? Should we be happy? I mean, we are happy for people who are alive survive a bad earthquake, right? Okay, but should we look for more? According to this distribution and our central limit theorem skill that you learn in Thomas class, we are sure that there must be more than 520 people. So finding 520 people should not stop our research, our search and rescue operation. That's how we use it. Okay, that's how we use it. Okay. That's how statistician, you will be useful in telling us, should we stop the search and rescue operation or should we go on, right? We may think, well, having 520 people is already enough, right? It turns out, no, that's not enough. Okay, that's not enough. We are sure there must be some other people need to be accounted for. Okay, I come from a country where earthquake happens a lot. And California also is especially Southern California. We actually live in fault lines, right? Okay, so earthquake is something we should anticipate. Okay, I will take a break right now. And starting from number 5, we get into confidence interval case. I will take a break. Let's say I give myself around 15 minutes. I will come back at 5:40. I will come back at 5:40. At that time, we will do the other. I think there are only 3 pages here. Yeah. No. Yeah, 4, 5, 6, 7. Yeah, so there are 4 more pages. But all of them short though. Okay. We'll continue later. Take a break first. Number 5, assume the assets of a family of 4 are normally distributed with standard deviation 120,000. So that's the sigma. The American Family of 4 Association, of course, this is a very hypothetical association, surveyed 60 families of 4. That's n equals to 60. And the total assets is $2.4 million. Okay, so what is the sample mean? The sample mean will be $2.4 million divided by 60, right? Divided by 60, that will be what? 40,000? Is it right? 400 times 6, yeah, 40,000. So that's the sample mean. Okay, so part A, construct a 95% confidence interval for mu, which is the mean assets of all family of 4. Step 1, best point estimate X bar equals to 40,000. If you don't show this here, then you need to show that computation here. Okay, you need to tell me how you get that 40,000. And then critical value, because the sigma is known, then we will use standard normal distribution. Confidence level 95%. Means the remaining 5% is being shared by two tails. This will be 97.5%. Okay, so the critical value is inverse norm 0.97501. It's standard normal distribution, right? So the mean is 0, standard deviation is 1. I believe this will give us 1.95996. Margin of error will be critical value times standard deviation over square root of sample size 60. Okay, 1.95996 times 120,000 divided by square root of 60. So the margin of error is 30,363.56976. That's the margin of error. Therefore, the 95% confidence interval for mu will be best point estimate 40,000 minus that number. Less than mu, less than 40,000 plus that number. So 40,000 minus 30,363.56976 will be 9,636.43024 less than mu, less than 70,363.56976. Yeah. Okay, so the mean assets of all for all family of 4 will be the mean. So between 9,600 to 70,300 something. Okay, I think it's not, I would like to have a larger sample size to have a better view on this. The interval here is way too big. But anyway, let's see part B then. Suppose that what sample size is needed to determine the mean assets for all family of 4 within $10,000. So the margin of error should be $10,000. But this time we want the confidence level to be even higher, 98%. You see the margin of error we have in the previous question? The margin of error we have in the previous question is actually very big, right? It's around 60,000. Okay, and the confidence level only 95%. So if the confidence level is even higher now, 98%, with margin of error even smaller, then the sample size must be a lot larger. Okay, must be a lot larger. Let's take a look. Let's take a look. So let's find out the critical value first. If the critical value, if the confidence level is 98%, so the remaining 2% is shared between two tails, okay, such that the critical value have the area to the left 99%. Okay, that's inverse norm 0.9901. That's 2.32 something. That's 2.32635. Now the minimum sample size, make sure you have this formula handy. The minimum sample size is 2.32635 squared times 120,000 squared, standard deviation being squared, right? Over margin of error 10,000 squared. Okay, the formula is the minimum sample size is the ceiling of critical value squared times the variance over margin of error squared. Okay, that's the formula. So then let's compute this. I get the ceiling of 779.31. That will be 780. Okay, that will be 780. That's the minimum sample size. So if you want to be this accurate with this high confidence, then you need to survey 780 people. Okay, 780, at least 780 families of 4, which is my situation. You know, me, my wife, and 2 children, right? Okay, so on average, you can tell that our assets is, if that's the result, then our assets will be, on average, will be between this number, in between these 2 numbers. Okay, let me go on to the next page, page 5. Estimating population proportion. A preliminary survey of 82 adults found that 51 of them are using Beeple product. That's just the Apple, the fake Apple. Okay, I make up a brand. Okay, so the N equals to 82, the X is 51. So later on, our P hat is 51 over 82. Okay, we want 95% confidence level. Step 1, best point estimate is P hat, which is 51 over 82. Let me make it decimal. That's 0.62195. Critical value, because that's proportion, we use standard normal distribution. That's inverse norm 0.97501. How do you get that, Thomas? Confidence level is 95%, means 95% in the middle. Okay, the remaining 5% is shared between by 2 tails, right? So the critical value has area to the left, 97.5%. The critical value will be 1.95996 again. Now, then how about the margin of error? Margin of error will be critical value times square root of P hat, which is 0.62195 times Q hat. Oh, let's prepare that in advance. What is Q hat? So Q hat will be 1 minus P hat, which is 1 minus 0.62195. That's 0.37805. Over sample size 82. Using calculator, 1.95996 times square root of 0.62195 times 0.37805 over 82. I get 0.10495. By the way, this is also the technique you can use to know if, in politics, for example, right? Do we have enough support for a certain candidate? Suppose you have this result here. Suppose you have this preliminary result here. Then will you go on with that person's candidacy? Okay. Well, actually, if it is close enough to 50%, and especially this one is more than 50%, I will go on. Okay. But imagine if the support is only 5 out of 82 people instead of 51, right? I don't think that person have a chance. Okay. Now part 3, step 3. So 95% confidence interval for population proportion. That will be the best point estimate minus margin of error less than P less than best point estimate plus margin of error. Using my calculator, it's 0.51700 up to 0.7269. Now, by the way, when you construct the confidence interval, I need you to write this step 1, step 2, step 3. Okay, I need you to write those steps. I need you to write that 1, 2, 3. Okay, don't get rid of that. Don't just write it this way. No. I need you to write me that 1, 2, 3. Okay. Step 1, step 2, step 3. Based on the preliminary survey result in part A, how many adults should we survey to determine the population proportion of adults using people product if the margin of error is 0.05 and confidence level 98%. So the margin of error is that's the confidence level. What is the critical value? 98% in the middle. The remaining 2% is being shared by 2 tails. So the critical value has area to the left, 99%. So Z critical is inverse norm 0.9901. That will be 2.32635. And then the minimum sample size will be critical value squared times sample proportion squared, which is, what's that again? 51 over 82. 0.62195. 0.62195 times the Q hat. $0.37805 over margin of error squared, 0.05 squared. Okay, the formula is N equals to the critical value squared times P hat times Q hat over margin of error squared. Okay, So basically, if you want to know a more accurate proportion of adult using B per product, you should do that preliminary survey first. Okay, and then you update your informations here to to improve your accuracy. Then we can tell, okay, then we need to survey how many people. Okay, now then I will compute that 2.32635 squared times 0.62195 times 0.37890. I'm sorry, 37805 divided by 0.05 squared. Okay, by the way, this E here, because it is for proportion, they may say that the margin of error of 5%. Okay, but you still need to make it 0.05. I get 508.9965. Well, basically, we will round it to 549. So you need a sample size of 509, at least. Okay, number 7. A student randomly samples 8 paperbacks at a store and find the following prices. Find the sum of X and the sum of X squared. So you need to show your work, right? Okay, you need to show your work. What is the sum of X? Let's use calculator. I show you how to use the calculator again. This is what I will do. I wonder if you remember that. I want to find the sum of X and the sum of X squared, okay? Of course, you need to show the work, right? But you can use calculator for this. What I will do is I will do stat, add it, and enter all the data. This time I will enter it to L3. Okay, the third column. 9.4 is the first data. 8.3 is the second data. 7.5 is the third data. And then 8.7. And then 9.4. And then 9.1. 8.7. 7.2. Okay, now you put this data in, right? And then you will calculate that. It's L3. The frequency list, I will leave it empty. Calculate. Doom. Okay, so from here you see the sum of X is 68.3. The sum of X is 68.3. How about the sum of X squared? 58789. 58789. That's for the sum of X squared. And that's it. You are done with this 3-point question. Right? Now, how about the mean? Now, this must be a sample mean. So the notation is X bar. Right? The sum of X, 68.3 divided by 8. Right? Go back to your calculator. If you divide that by 8, then it must be X bar. This X bar, 8.5375. 8.5375. Or you can just use your calculator and divide these two numbers, 68.3 divided by 8. You should get this 8.5 something. Okay. And to find the standard deviation. The standard deviation, if you see the calculator here, will be 0.826 something, right? But you need to show the work though. So let's show the work first. And we use the result from calculator later on to confirm. This is 8 times 587.89 minus 68.3 squared over 8 times 7. N times n minus 1 on the denominator. Okay, now then I use my calculator to compute that. 8 times 587.89 minus 68.3 squared divided by 56. I get 0.68268. So the sample standard deviation is square root of this number. Which will give me 0.82624. Let's compare what I get. See, 0.82624. Right? Okay, so my calculator confirmed my manual computation. Now, assuming the price of paper bags are normally distributed, because our sample size is less than 30, we cannot use the procedure that we had earlier unless the underlying distribution, in this case, the prices of paper bags, are normally distributed. Okay, construct a 95% confidence interval for the population standard deviation. Oh, okay, for the population standard deviation. So that will be step 1, I need to do chi-squared right. Step 2, I need to do chi-squared left. Right? Okay, that's chi-squared distribution. It's skewed to the, it's non-negative and skewed to the right. 95% in the middle. The remaining 2.5% is shared by the tail. This is chi-squared right. This is chi-squared left. Now, chi-squared right will be inverse chi. Remember the chi-squared program? And then the area to the right, this is 0.025. Degree of freedom is 7. Okay, go to program, inverse chi. Area to the right, 0.025. Degree of freedom is 1 less than sample size 8, right? So this is 7. Compute 16.01276. That is 16.1276. Now chi-squared left is inverse chi. Area to the right, 0.975. Degree of freedom, 7. So let me start the process again. Area to the right, 0.975. Degree of freedom is 7. 1.68987. 1.68987. Okay, now then step 3. 95% confidence interval for population variance. That is degree of freedom 7 times sample variance, which is 0.68268 over chi-squared right, 16.01276. Less than sigma squared less than 7 times 0.68268 over 1.68987. And I use my calculator to compute that. get on the left-hand side 0.29843 less than sigma squared less than I get 2.82789. Now then the question is population standard deviation, confidence interval for population standard deviation. Then I apply square root to each side. Right, that's square root of 0.29843 on this side. And this is square root of 2.82789. This is 1.68163. And this is 0.54629. Okay, but you need to do the confidence interval for variance first before you do confidence interval for standard deviation. Okay, you need to do this first, and then you go on doing the square root. Do not do the following. I have seen students did this in the past. In the thing is like in the past, I didn't emphasize that, but in the past, I have seen students that did this right away. So from here, get to this right away. No, that's not appropriate, okay? Yes, you get the answer really fast, but when it comes to confidence interval for population standard deviation, you always need to, it's just tradition. You always need to go through the confidence interval for population variance first, okay? Now, let me go on the last page. A survey of 37 Math 227 Test 2 scores in Thomas's classes result in confidence interval of 54 to 62. If the sigma is known to be 10, find the confidence level by doing the following steps. First one, what is the best point estimate, X bar? So what is the average of these 37 people? Well, the average will be 54, the midpoint of the confidence interval. Okay, that's 116 over 2, that's 58. Now imagine this is your confidence interval. The lower bound 54, the upper bound is 62. The midpoint must be the X bar, right? That's 58. How about the margin of error? Margin of error will be, we know this is 58. So 62 minus 58, that's equals to 4. This is the margin of error, the distance between midpoint and the upper bound, or the midpoint and the lower bound. That's also margin of error. Okay. Now then, part C, find the critical value. The critical value, use the formula in step 2. Critical margin of error equals to the critical value times population standard deviation over square root of sample size. The margin of error is known to be 4. Critical value is the one we are looking for. Population standard deviation is 10. And sample size is 37, square root of 37. Okay, so 4 times square root of 37 over 10 equals to the critical value. That is 2.433105. Call that 1. That's the critical value. Okay, now then, what is the confidence level then? The confidence level, let's sketch that first. Okay, we have this critical value, 2.4 something, right? Critical value is 2.43311. While we want to find the confidence level, which is in the middle. Now, this must be the opposite of that, right? Which is negative 2.43311. Now, the area in the middle here is the confidence level. But the area in the middle there is the probability with lower bound, upper bound given. So the confidence level is equals to normal CDF negative 2.43311 to 2.43311. Using my calculator, I get 0.98503, approximately 98.5% confidence level. It's more than 98%, it's less than 99%. Okay, now that's for this solution for winter 1. Okay, now I will stop the discussion here. Let me remind you that this Wednesday you have a test. And I went over with winter 21 just now. We have this one here. We have from fall 20 last Wednesday, right? So you go to the discussion from last time, April the 28th. Is it April 28th? Yeah. We went over the fall 20. Okay. And for your own study, spring 19. Right? Take a look on those. That's for your this Wednesday. Now, after the test, and ask yourself if you want to stay in this class or you should drop the class. Okay, of course, I hope you stay in this class. Okay, but just in case you want to avoid an F or even a D, then drop the class. Okay, but if you stay in this class, I hope during this weekend, basically after the test, I want you to watch this lecture video here. The second half of lesson 18, you watch it from after the first hour, starting from here, let's say, and lesson 19 also. Watch these two before Monday, okay? But just do this after your tests, okay? I hope you do well with your tests, all of you. I hope you do well with your tests, and basically just finish this class and then transfer. Okay, that will be the best, okay? That's all I want to say. Then see you on Wednesday.